Good morning, everyone. For our first episode of Net Talk, we will be discussing the topic measurements and uncertainty. What is measurement and uncertainty? As engineers, measurements will have some sort of uncertainty. Usually, we take measurements to calculate exactly how big or what the scale is of a certain object, as you can see over here. Let's say, for example, we need to measure how big this pencil is. We should know how to read and communicate this measurement very effectively. This could be our own work, for example, or someone else's. If we were to measure how tall this pencil is, you could easily say it looks like 9 centimeters. However, in reality, the pencil may not be exactly 9 centimeters. It could definitely be about that measurement, but it could also be 8.9 centimeters or 9.1 centimeters. We would never be able to know exactly how tall this pencil is because measurements will always have an error about it. Whether there is an error with the ruler or whether we make a mistake when measuring it, as we are all human, of course. So therefore, since there will always be an error in terms of measurements, we call these uncertainties. In this case, you could say the uncertainty will be plus or minus 0.1 centimeters, as this measurement, 8.9 centimeters, is obviously 0.1 centimeters less than the original thought measurement, which is 9 centimeters over here, or this measurement, 9.1 centimeters, is 0.1 centimeters above the original thought measurement, which is 9 centimeters. Don't worry, we will discuss everything more in depth about measurements and uncertainties later on in the video. What do we need to know? Well, one thing is important is we need to know the level of accuracy. This means we may need to know how accurate our measurement is as much as possible. What we will also need to know is it accurate enough? How accurate is our measurement? We will also look at how the level of accuracy affects further calculations. Moving on. What is accuracy, you may ask? Well, accuracy is how close the measured value is to the true value. For example, let's say this stick is measured at 5 centimeters. If we make a reading of 4.5 centimeters when measuring it, that is not quite accurate. But if we make a measurement of 4.9 centimeters, you could argue that is a little more accurate and closer to the true value of this stick. Therefore, the accuracy of this measurement is higher compared to this, which is not exactly accurate. What is precision? Some of you may confuse precision with accuracy, but that is wrong. Accuracy, as I mentioned before, is how close a measured value is to the true value. But precision is how often accurate results are obtained. What does this mean? Let's bring the stick back into play. Let's say our target is to make 5 measurements of this stick. And the reason why we are making 5 measurements is because the more measurements you make, the higher the chances that you're going to find an average value for the true measurement of this stick. So let's say, for example, we make 5 measurements. We get 4.9 centimeters on the first measurement, and 5.2 centimeters on the second measurement, then 5.1 centimeters on the third measurement, and as follows, 4.9 centimeters on the fourth, and 5 centimeters on the fifth. You could say that this set of measurements are quite accurate. Why is this? Because there is only 0.1 centimeter difference, except this case, which is only 0.2. And the fact that almost all 5 of these are very accurate, we call this high precision. Whereas, for example, if we were to have low precision measurements, they would look something like this: 4.5 centimeters on the first measurement, 4 centimeters on the second measurement, 5.1 centimeters on the third measurement, 5.4 centimeters on the fourth measurement, and 4.6 centimeters on the fifth measurement. As you can see, these measurements are quite far from the true value, of the 5 centimeter stick, except for this one, of course. That we did get quite accurately. However, the rest are quite far from the true value. In this case, we call this low precision. Next, we will move on to errors. It is very important to understand that errors are not mistakes. An error does not mean that you have had a mistake. What does it mean, though? It means that there is a small difference between the true value and the measured value. This gap between the true value and measured value is known as the error. If you have made an error, and if the size of the error is known, a correction can be applied. However, if you make a mistake, you will never know. Therefore, these two concepts are very different. Next, let's move on to where does uncertainty come from? As mentioned before, no measurement is perfect. Each measurement is slightly different almost every time, if not every time. Even if it is done by the same person, and even if they are using the same tool. In this case, if an error is caused by the same person using the same tool, we likely call this as human error. And this concept can be considered as type A uncertainty. However, if there is an issue with the measuring device, we call this type B uncertainty. These are the two types of uncertainty that we will learn about more in the video. Firstly, let's dive deeper into type A uncertainty. You can find type A uncertainty using standard deviation. The formula for this is quite simple. Standard deviation is found using this formula. In this case, n is the number of times a measurement was taken. In the previous scenario, where we were measuring the stick, we measured it 5 times over here. Therefore, n in this example would be 5, which we will write in this place. And that 5 would therefore, after minusing 1, would equal to 4. You're probably wondering, what happens here? What is reading and what is average? Well, reading is the true value of this stick. If this stick is really valued at 5 centimeters, and if this was our set of measurements, then we will have to find the average of these readings. The average of all 5 readings would equal to 5.02 centimeters. Therefore, we do have the reading and we have the average. So in this case, the reading is 5 centimeters and the average is 5.02 centimeters. In this case, it's quite simple. Now we have our reading, we have the average, and we have our number 4 over here. Therefore, we can simply put it into the calculator. 5 minus 5.02 over 4, whole thing square rooted, which gives us a value of 4. Well, that's unfortunately not possible. I just entered it into the calculator. And I think that is because we made a mistake. We forgot the square over here. If we enter the square, we will get the correct answer. 5 centimeters minus 5.02 centimeters square over 4, whole thing square rooted. Now we should be able to get the correct answer. Yes, we do. The final answer for the standard deviation only is 0.01 centimeters. Next, let's talk more about type B uncertainty. Type B is usually found from other information such as the accuracy of the instrument used. Usually, this number will be displayed on the instrument that you are using. For example, if you are using a vernier caliper, which would usually look something like this, it'll give you the uncertainty on the device. For example, let's say the uncertainty of this device is plus or minus 0.02 millimeters. That means to whatever measurement you make, there could be a difference of 0.02 millimeters to the measurement that you actually find. As mentioned before, this number would usually be displayed on the measuring device. So to calculate the type B uncertainty, we will have to use this, we will have to use this number, and we will consider that number as the half range. So 0.02 will be known as the half range. So to find your type B uncertainty, it is equal to the half range divided by square root of 3. So in this case, the half range would be known as I'm sorry, the type B uncertainty would be known as 0.02, which is the half range, divided by square root of 3, which is equal to 0.012 millimeters. So you have your type B uncertainty here. You have your type A uncertainty here. What's next? Well, the job is not done. Now, we have to combine our uncertainties. After we have both our type A and type B uncertainties, we cannot just add them together. We need to use this formula. Combined standard uncertainty or CSU for short, is calculated by the type A uncertainty or square of your type A uncertainty plus square of your type B uncertainty, whole thing square rooted. This is how you find your combined standard uncertainty, or SCU for short. So let's calculate our combined standard uncertainty. As previously shown, our type A uncertainty is 0.01 millimeters, if I'm not mistaken. Sorry, 0.01. Let's consider this as millimeters to make things easier for ourselves. Let's pretend that was never centimeters. So 0.01 millimeters. Then we have to square that and then add it with the square of our type B uncertainty, which is 0.012 millimeters. And then square root that, which should be equal to our CSU, or combined standard uncertainty, which the end result would be again 0.016 millimeters. It's very close to these two values here. So that is how we find our combined standard uncertainty. However, it is still not the end of the road, as after finding our combined standard uncertainty, we will need to find our expanded uncertainty. To find our expanded uncertainty, we will need to multiply our CSU over here by a coverage factor. Now, what is a coverage factor? Well, I will explain that very shortly. To make things easier for us, I will write down that expanded uncertainty is equal to CSU multiplied by the coverage factor. So as promised before, I told you, I will explain what the coverage factor is. Coverage factor is a certain area of measurement. You have three options: coverage factor 1, coverage factor 2, and coverage factor 3. So the coverage factor 1 you will get a 60% chance of getting the right value or the right error. With coverage factor 2, you will get a 95% certainty. Coverage factor 3, you will get a 99.8% certainty. These, or rather each value, is the probability that the true value lies within the range. Usually, when people who are buying a product want a high true value probability, they would usually ask for a coverage factor of 3. So let's multiply our let's multiply our combined standard universe, combined standard uncertainty by a coverage factor of 3. So that would mean 0.016 millimeters times 3, which is equal to 0.048. This is our expanded uncertainty. All right, we are almost done now. Our final results. So our stick has an average measurement of 5 millimeters, as mentioned below. So 5 millimeters will be the true value. But we also have to add our uncertainty to the value, because it's not exactly 5. Therefore, that's where we bring in the expanded uncertainty. So the final value, or the final measurement, would be like this. 5 plus or minus, we use this value, 0.048. Millimeters. The units comes after the uncertainty. And this is your final answer. Thank you for watching the video. Please like and subscribe, and share this video among your friends who aspire to become engineers or get better with their studies. Thank you for watching.